Hi everyone, my name is Lydia and this is what I wish that taught me about econometrics and introduction. In the previous video, we established the classical measurement error in y does not bias the slope coefficient. Now let's verify that with a concrete numerical example and see exactly what does change. So suppose the true model is income equals to 20 plus 3 times education. And then we're going to have an error term in here, U. Okay, so keep in mind here, I'm not putting income hat, okay? That's why I can put the error term. If I had put the hat, then this would have been out of the picture, okay? So interpretation in terms of the 3 that we have in here is that every additional year of education increases my annual income by 3. Let's say income is in thousands, so by 3,000. We estimate this using perfectly measured data, and the OLS gives us beta 1 hat equals to 3.02, okay? So as you can see, this is very close to the true value of 3. This is what we'd hoped to see. In a real data set, we'd never get exactly 3. There's also sampling variation. And the sampling variation means that the estimate fluctuates, but it is still centered around the truth. Okay, now suppose income is instead self-reported. So let's say people who underreport, let's say if their true income is 50,000, they underreport 47,000. Individuals could overreport when they have a lower income, let's say from 30 to 33K and so on. So the errors would be random. Some maybe who have also higher income would also be overreporting. Okay, so there is a classical measurement error in here. So in this case, we would write the y equals to y star plus some error v, okay? And v is this random noise. Now, education is still measured perfectly. The only thing that has changed is how accurately income is recorded. And this is, remember, the key setup, because X is clean. Only the Y has been contaminated, and everything that follows, it's basically coming from this particular point. So let's say that we run the regression using the noisy data. Okay. And let's say we have a beta 1 hat that now gives us 2.98. Okay. Did the slope change dramatically? Not really. Like, it moved from 302 to 2.98. The difference seems to be quite trivial. The slope is essentially still 3, the true value, and the measurement error in y has not really biased the coefficient. Now, if we repeated this many times with different random errors, okay, the average estimate would be exactly 3. Okay, because the estimate fluctuates around the truth, it wouldn't drift away from it. But something has changed, okay? Because what is happened in here, if we compare the regressions and if we had further information on what's happening on the residuals, on the perfect y, which would be this case right here, for the perfect y, where the beta was the 3.02, you would have had, let's say, standard error of 2.1, okay? While, instead, let's say, a residual standard error of 2.1, and let's say you also had a standard error for the beta 1 hat of 0.08, and let's say that you also had an R squared of 0.81. Now, what's going to happen in the noisy data, the actual numbers that you're going to see, is beta 1, 2.89. You would have seen that the residual standard error would have been something greater, let's say 4.3, you would have found that the standard error of the beta one in here would no longer be that 0.08, but 0.16, let's say. So you see double. And your R squared now would have been not 81%, but something a lot lower, let's say 0.54. Okay, so while the coefficient is almost unchanged, everything else in here is actually changed. The residual standard errors have roughly doubled. The data are much noisier around the line. The standard error has doubled. We're less certain about our estimate, and the R square has fallen because the noisy Y is harder to explain. Okay. And the doubling of the standard error is directly interpretable because with noisy Y, confidence intervals are roughly twice as wide. So we need more data to achieve the same precision. Now, why does this happen? So the measurement error V only moves observations up and down, as we showed in the previous video in the graph. So it doesn't change their education level. It doesn't shift them left or right. Okay, so it's just up and down. So OLS still identifies the same averages between and like in the relationship between education and income. So the noise makes it harder to see, but not impossible. Okay, so think of it as looking at stars through the fog. The stars have not moved, the fog just makes them harder to see clearly. Okay, and with this number, we had like a concrete example of like what your numbers would have looked like in terms of like consequences when you use data that is affected by measurement error in the Y. Now, remember, this is the good type of measurement error. It's noisy, but not biased. Unfortunately, when measurement error occurs in the independent variable X, the regression behaves very differently and will be introduced to something that is called attenuation bias. So stay tuned, and I'll see you in the next video.